Good afternoon, students. In the last lecture, we talked about the postulates of quantum mechanics. We talked about the first postulate where we said that in quantum mechanics, there is a wave function psi, which is a function of the space coordinate and time that carries all information about the system. We discussed about the mathematical properties of the wave function, and we also talked about the physical significance of the wave function, where we saw that the mod psi square of that function gives us the probability of finding the particle per unit volume, and that is what we call the probability density. Then we also talked about the normalization condition. Now today we will talk about another postulate of quantum mechanics, which is related to what I have written here, operators in quantum mechanics. So in quantum mechanics, all dynamical variables related to the evolution of a system that is represented by linear and Hermitian operators. Now before we talk about linear and Hermitian operators, let us understand what is an operator. So what are operators? They are nothing but operators. They actually perform some mathematical operation on a function. So if a is a dynamical variable, then it can be represented as a cap. Now a cap operating on a function fx is equal to some constant into another function gx. Now this a cap operating on fx can give a new function gx, or it can give the same function fx back, and c here is the constant. So let us take one example. So if a cap is ddx, the a cap operator is written as ddx, and the fx function I take it as x square. Now if I operate a cap over fx, I will get ddx operating on x square, and the answer is definitely, all of you know, is 2x. So here this 2 is that constant c, and this x is a new function gx we have got. So fx was x square, a cap operates on fx to give us another new function x into this constant. If we take another example, that a cap remains ddx, but the function fx is e to the power 2x. Then what we get? If we operate a cap over fx, the answer we get is 2 e to the power 2x. So here now we get back the same function. The operator operates on this to give us the same function back. When we have a situation like this, that a cap operates on fx and we get back fx, then this fx is called the eigenfunction, and this c, which is a constant, is called the eigenvalue, and a cap is the operator corresponding to that. So this is the idea of operator. Now in quantum mechanics we are saying that the operators are linear and Hermitian. So first let us understand what is meant by a linear operator. If I say that a cap operator is a linear operator, then a cap operating on fx plus another function gx will give me a cap fx plus a cap gx. And the second condition is that a cap operating on some constant c into fx, the result will be the constant c into the operator a cap operating on fx. So if these two conditions are satisfied at the same time, then I will say that a cap is a linear operator. And in quantum mechanics, most of the operators that we will be dealing are linear operators, because, and these operators, what is the utility of being linear operator is that the superposition principle is maintained. So if fx is a solution of the linear equation and gx is also a solution, then I can say fx plus gx is also a solution. So this will be helpful if the operators are linear. So let us now give one more example. So if the a cap operator is, say, minus I here is the imaginary number, h cut is, h by 2 pi into ddx. Okay. So this h cut is of course a constant. Now I want to examine whether this operator is linear or not. Then what I do? This is the operator, I operate it on fx plus gx. So if I operate it, what I get? Minus I h cut is constant. ddx operating on fx is df dx. And again minus I h cut, dx operating on gx is dg dx. So here you see now minus I h cut ddx is my a cap operator. So a cap fx plus again minus I h cut ddx is a cap operator. So plus a cap gx. So the first condition is satisfied. A cap operating on fx plus gx gives me separately a cap operating on fx plus a cap operating on gx. Now the second one, let us see. So minus I h cut ddx operating on cfx. So c is a constant. So of course the constant will come outside and it will be minus I h cut c df dx. So this will be equal to c a cap fx. So both the conditions are satisfied. So I can say that this is a linear operator. So this is the concept of linear operator. Now as we proceed, I will be giving you problems where you will be just justifying whether a given operator is linear or not. Now another property of the operators in quantum mechanics, which I said, is that it is Hermitian in nature. So let us talk about what are Hermitian operators. So Hermitian operators, so I will say that an operator a cap is Hermitian if the following result is satisfied. Psi star a cap psi dx, if that is equal to integral psi a cap star psi star dx. So if this, so integration is over the limits of x, I just keep it. So if this is satisfied, then I will say that this a cap operator is a Hermitian operator. And there are numerous examples of the operators being Hermitian. Now what is the utility of this Hermitian operator? So if the operator is Hermitian, then the eigenvalues which I was speaking of just now, that a cap operating on fx, if I get some constant into fx back, then this constant c, I call it the eigenvalue. So if we will prove it later on. Actually I will be discussing postulate 3 and then we will be proving that if my operator a cap is Hermitian, then this eigenvalue will always be real. And it is important for this eigenvalue to be real because this eigenvalue actually gives me the possible values of this operator which I am measuring. The operator is actually representing some dynamical variable. So whatever dynamical variable I am measuring, the possible outcomes of that variable are actually these eigenvalues. So you can think that for a solution or for an outcome to be physically viable, it's important that the result remains real. So it is important that the eigenvalues remain real, and if your operator is a Hermitian operator, then these eigenvalues will always remain real. So this is what I mean by operators being linear and Hermitian. Now next what I want to discuss is what are the operators that you will be dealing with in quantum mechanics. What are the common operators that you will be needing in quantum mechanics? So let us talk about that. So the list of operators which you need to know to proceed further with this course on quantum mechanics and to study the application of Schrödinger's equation and so on. So here I am writing the dynamical variable, and so you can take down in the form of a table, and here I am writing the operator representation of it. So let us first talk about the dynamical position, the dynamical variable position, right? So position usually we denote by what? If it is in one dimension, by the either x, y, z. In 3 dimension by the r vector. So how will you represent it in the operator form? So r will be represented as r cap. Simply the r vector will be represented as r cap, and x, y, z are simply x cap, y cap and z cap. Okay. So this is the position representation. Next let us talk about momentum. So momentum we denote it usually as P. Now in the operator form we will write P cap is equal to minus I h cut the gradient vector in 3 dimension. Okay, so h cut is h by 2 pi, and this gradient vector means, now this I here is the imaginary number I, and the gradient vector all of you know is I cap del del x plus j cap del del y plus k cap del del z. There that I cap is the unit vector I cap, unit vector j cap, unit vector k cap. So now if you want to write down the components of this in the x direction, y direction, z direction, how you will write? So px cap, in that for the x direction we will represent as px cap, and that will be minus I h cut del del x. Py cap will be minus I h cut del del y, and pz cap will be minus I h cut del del z. So this is the momentum representation along the x direction, y direction, z direction. Okay. Next we will be talking about the kinetic energy operator. The kinetic energy operator. So we know kinetic energy is represented by p square by 2m, where m is the mass of the particle. So the kinetic energy operator T cap will be p cap square by 2m. Now p cap is, you know, minus I h cut gradient vector. So if you do the square of that, I square h cut square grad square by 2m. I is the imaginary number, so I square is minus 1. So minus h cut square by 2m grad square. Okay. And similarly in one dimension you can write minus h cut square del 2 del x square and so on. So this is the kinetic energy. Next is the potential energy. So the potential energy is V. So it is usually, for the problems that you will be dealing, you will be taking it as a function of the space coordinate. So it simply remains as VR, and if it is in one dimension then Vx, V as a function of x or y or z. Now we will talk about the Hamiltonian. So the Hamiltonian represents nothing but the total energy of the system. Because when this potential energy is a function of the space coordinate only, then the Hamiltonian is nothing but the sum of the kinetic energy and the potential energy. So now the Hamiltonian operator will be simply T cap plus V cap. So T cap is minus h cut square by 2m grad square, and V cap is VR. So this is how we will represent the Hamiltonian operator. Now there are some more operators, mainly the angular momentum operator, which I want to discuss, but maybe that we'll discuss in the next class. But you can write down this Hamiltonian operator in one dimension. Just let me write it at least for the x motion. It will be del 2 del x square plus Vx. So this is the postulate 2 of quantum mechanics, but a little bit more is left to discuss in postulate 2, which I will be continuing in the next class. Thank you.